Let's do a quick recap and we shall proceed further. So we started talking about ensemble techniques and what are the benefits of ensemble techniques. It will help us improve the accuracy and also it will help us improve stability in the models. These are the two advantages of any ensemble technique. And ensemble technique is all about allocating the data set, training data to different models. And then you build different models and you combine the different models. And then you get the final result. Okay, next. Ensemble techniques are used to handle bias, variance, trade-off. The explanation pertaining to bias and variance, etc. is given. Then we discussed that we have non-generative models and generative models. And when it comes to voting, we spoke about hard voting and soft voting. Soft voting is very similar to taking an average. When it comes to average, you have simple average and weighted average. And then we also have stacking, which we are yet to discuss. We will discuss in today's session. When it comes to generative models, we spoke about bagging, random forest, and boosting. Within boosting, we discussed AdaBoost. These two are homogeneous in nature. Okay. For that case, even boosting would be homogeneous. Or let me put it this way, generative models are homogeneous in nature. Non-generative models are heterogeneous in nature. When it comes to homogeneous algorithms, you can either have tree-based algorithms, that is all decision tree models, or you can have non-tree based models, all non-tree based models such as KNN, etc. Okay. Hard voting is also called as max voting or majority voting. We've already spoken about that. Then stacking, we'll get to stacking. Today we need to talk about stacking as well. Okay. But stacking would come towards the fag end, and then we'll talk more about that. When it comes to sampling techniques, we have non-probability based sampling techniques, which is based on the judgment of the user. And we have probability based sampling techniques where we have simple random sampling, stratified sampling, systematic sampling. And we have discussed about all of these in detail. We also spoke about holdout method, leave one out cross validation, k-fold cross validation. And we had some discussion around that. Then we discussed about bootstrapping. Bootstrapping is sampling with replacement. We spoke about bagging. Bagging is nothing but bootstrap aggregating. Bootstrap aggregating. And we know for a fact that 36.8% of the instances or rows would not be selected in your training data when you continuously keep splitting the data. And the data which is not part of your training data set is also called as out of bag data set or out of sample. And approximately 36.8% of the observations will not get selected in the training data. Next, we discussed about random forest. And And when it comes to random forest, did we not mention it here? When you deal with regression problems, approximately 1/3 of the features get selected whenever you split. And when it comes to classification kind of problems, it is root P. Okay. And within boosting, we spoke about ADA boost. Within ADA boost, when it comes to decision tree, you go ahead with decision stumps. Decision stump means decision tree with maximum depth equal to 1. Only once the split happens. That's it. Okay. And we are supposed to talk about gradient boosting, extreme gradient boosting. Once we complete the discussion pertaining to these two, then we will get into stacking. With that, we will conclude all of the ensemble techniques and we'll get into the practical, Python programming aspects of it. And when we get into Python programming, that is when I'll probably try to do a recap in a better detailed manner. Okay. So let's get into gradient boosting. Gradient boosting is one of the boosting algorithms. And understanding this is important for us to understand extreme gradient boosting. The underlying working of gradient boosting and extreme gradient boosting is more or less the same. But then why people prefer this is something which we are going to talk about. Okay. When it comes to parallel processing, you can use bagging and you can ensure that multiple processors execute different algorithms in parallel. When it comes to random forest, you can have multiple processors run different algorithms in parallel. Within random forest, you'll have trees, decision trees. So multiple decision trees are processed in parallel. However, when it comes to boosting algorithms, we have discussed about ADA boost. And what ADA boost does, it will look at the previous algorithm, it will look at the errors, mistakes done, and it will give more weightage to those mistakes for the next iteration. So there is a dependency of iteration 1 on iteration 2. There is a dependency of iteration 2 on iteration 3, so on and so forth. The dependency will keep on increasing. So since there is dependency of iteration 1 on iteration 2 on iteration 3, we cannot perform parallel processing. Parallel processing is not possible. Not just for ADA boost, for any of the boosting techniques, parallel processing is not possible. Hence, what extreme gradient boosting does is it will make use of your hardware resources and your operating system to make use of certain operating system related parallel processing activities. And that is what makes extreme gradient boosting a very exciting algorithm. Okay. Yesterday, one of our friend was asking us a question on, can I use AdaBoost for regression-based techniques or should I use AdaBoost only for classification? The answer is AdaBoost is only applied when you have classification problems. Whereas the other boosting techniques such as gradient boosting and extreme gradient boosting can be used for both classification as well as regression problems. Okay. So here, AdaBoost is math intensive, whereas gradient boosting is not math intensive. Gradient boosting builds each base learner, that means each if you look at the errors and then do it. AdaBoost also has done the same thing, but what AdaBoost has done is it has looked at the previous learner's errors and it has given more weightage. Okay. And gradient boosting uses decision trees of varying depths. AdaBoost uses gradient decision trees with what depth? Yes. With depth equal to 1. This is also called as what? Decision stump. Decision trees with depth equal to 1 is called as decision stumps. So gradient boosting algorithm for regression purposes, it starts by calculating mean of the target variable for the training set and uses that as the initial prediction. Okay. Say you have a data set wherein you have output variable, which is to predict salaries of data scientists, and you have various inputs. Say you have 1,000 observations. You take each of that value, and then you can take an average of that value. You can take average of the output variable. Okay. This average becomes the baseline model. This is usually called as a baseline model. What do you mean by a baseline model? If I don't want to build any prediction model, and if you give me a new set of inputs, and if someone asks me, hey, what do you think will be the output for those new set of inputs? Like say I have a person's educational qualification, number of projects that he has worked upon in space of data science, and number of certifications that this person has. Given these 3 inputs, if someone says, can you predict me on what will be the salaries of data scientists? And if you don't want to build any prediction model, do you know what? You can simply take average of salaries of all the other people, and you can say that this will be the output. Give me any set of inputs. I'm just going to give you an average and say that this will be the salaries of data scientists. And your models that you build, prediction models, should always be better than the baseline models. It should always be better than your baseline models. Okay. Instead of output variable being continuous or numeric, what if I were to use output variable, which is categorical? Then how would you take the baseline value? The person will default or not default. Since we are sticking to that example, let's continue with that. Say you have 3 inputs. In this, assume that 20% is default and another 80% is non-default. When you give me new set of inputs, if you don't want me to build any prediction model, yet comment on what will be the output, then I'll just take the majority class. Okay. We'll just take the majority class and we'll say this is going to be the output. So this will be called as what? Baseline model. So when it comes to output variable, and if it is numeric, we take an average of that. No matter what the new set of inputs are, we just give average as an output. That's called as a baseline model. And when you have categorical data, you go with majority. If you have more than 2 classes, you go with plurality, meaning whichever class has the maximum percentage, that would be the output. Those models are called as baseline models. And your prediction models, machine learning algorithms that you use, should be giving you results which should be better than the baseline models. Final results that we get should be better than the baseline models. Yeah, imbalanced data sets, yes. You do oversampling, undersampling, whatever you want, whatever are the techniques. Smooth, modified smooth, right? Cluster-based techniques, ensemble techniques, all these are techniques to handle imbalanced data sets. Okay. In this scenario, if at all you build your prediction model accuracy should be greater than. If you build a prediction model, it should be greater than baseline. So your prediction model prediction should be greater than 80%. If at all you build your machine learning algorithm, then your accuracy should be greater than 80%. It should be better than your baseline model. Okay.